What if we're analyzing data that is numerical? What if we're getting a number from each element of our sample? We're measuring the height of each person in our sample, the weight of each lab rat in our sample, the amount of time it takes each person to solve a puzzle, the distance of each college student from home in miles, the diameter of a tree, the mass of a star, the temperature at each location in our sample. These are all cases where we're going to get numerical data, a number. We're not just getting binomial data, a yes or a no, a true or a false, colorblind or not, that sort of thing. We're not getting categorical data where it's either Coke or Pepsi or Mountain Dew. No, now we're getting a number from each individual thing in our sample. How do we analyze that? Well, first thing we're going to do is we're probably going to find our sample mean. So x with a line over it, x bar, represents the average of our sample. And we'll also want to compute our sample standard deviation. That's an S there, so that describes how spread out our data is. Now, here's the cool thing. If our population is normally distributed, so I've randomly gathered a sample of n items from some normally distributed population out there, and this population has a mean mu and a standard deviation sigma, what would happen? What will that look like? Well, if I did this a whole bunch of times, gathering many different samples from this, and each time taking the sample and gathering and measuring my sample mean x bar, what I'll get is what we call the sampling distribution, where all those x bars are. If I make a histogram showing the distribution of all those x bars, what I'll have is the sampling distribution of the mean. And what I will find is that if I'm gathering this from a normal distribution, then all those different x bars will form a normal distribution as well. The peak, the center, the mean of that sampling distribution will be the same mean as the whole population. I'm just as likely to get a sample with a sample average above the mean as below the mean, so that's going to be a nice symmetrical distribution there. However, when I do this, my x bars are much more likely, my sample means are much more likely to be clustered close to the mean of the whole overall population. And the larger my sample is, the more likely that they're all to be clustered around close to that. So we're going to have a smaller standard deviation. The sampling distribution, that histogram of all those sample means, those x bars, will be a lot narrower than a histogram of the whole population, because if I've got a sample, well, then, I may have a couple of large numbers in the sample, but they're decently likely to be balanced by a couple of small numbers in the sample. So there isn't going to be as much scatter, as much variation in all those different sample means x bar as there would be if I was just making a histogram of a bunch of data from the population. And what I find is that the standard deviation is lower by a factor of the square root of n. The standard deviation of all those x bars is going to be the standard deviation of the sample divided by the square root of my sample size n. All right. The central limit theorem is probably the biggest miracle, the most wonderful, glorious, fantastic, amazing thing that happens in all of statistics. The central limit theorem says that if I add up many different random numbers, and they're all independent of each other from some population out there, and this population has some mean and some standard deviation, all that sort of thing, then my sum, the distributions of my sum, will be normally distributed itself, even if the population is not normally distributed. That's surprising. That's shocking. That's interesting. I love this little graphic here where it says, okay, on the left, suppose you've got some population which is not normally distributed. In this case, we've got, we would call this a bimodal distribution. It has two peaks. So this is definitely not a bell curve. That's not a nice, simple, beautiful, lovely, normal distribution. But if I gather samples from that, I gather a sample of size n from that, and another sample of size n from that, and another sample of size n from that, the distribution of all my sample means, all my x bars, is going to form a normal distribution, even if I'm drawing from a population that is not normally distributed, as long as the sample size is larger than about 30 or so, and that there's no crazy, particularly insane outliers in it. That's amazing. That's wonderful. So that means as long as my sample size is more than about 30 or so, I can use the normal distribution. I can use the z distribution. I can use normal statistics, which is simple and straightforward, and we know how to deal with that. I can use normal statistics to analyze my data, to make confidence intervals, to do hypothesis tests, even if the population is weird, even if the population is strange and not simple and not a bell curve and not, symmetrical and all that sort of thing, as long as my sample size is larger than 30. If I were to do many, many, many samples of that, though the averages of all those samples would form a nice, beautiful Gaussian normal distribution. That is a glorious, fantastic miracle, and that allows us to do all sorts of wonderful analyses of things which otherwise would be really, really hard. So here's what I want to do. I want to use the normal distribution to analyze my x bar, my sample mean. I can do this as long as either the underlying population is approximately normally distributed, if I have a small sample, or if my sample size is larger than 30, then it doesn't matter how that is. That's wonderful, that's glorious, that's fantastic. But the problem is, in order to do my analysis, in order to do my confidence interval and my hypothesis test, all that sort of thing, I need to compute the standard error. The standard error is sigma, the population standard deviation, divided by the square root of the sample size. Well, I know what my sample size is, but how would I know what sigma is, the standard deviation of the whole entire population out there? I would have to measure every single thing in the whole entire population in order to calculate what the standard deviation of the whole population is. But that's the point. The whole point of inferential statistics is I'm going to use a sample to say something about the population. And even though I don't have the whole population, I can say things about it based on my sample, but I don't know what the whole population is. So what can we do? We're going to make an approximation. We can't use sigma, the population standard deviation, because we don't have that. We can compute the standard deviation of my sample. That's an S. So notice we've got a Greek letter sigma to represent the population because, that's the whole population. That's Greek to me. I don't have that. Whereas for my sample, I use an English letter S because I know English. I speak English frequently. And so that S represents the standard deviation of just my sample, of just the data I have in my computer. So I can make the approximation. Okay, the standard error is sigma, the standard deviation of the population, divided by the square root of n. I don't have that, so this is approximately equal to my sample standard deviation S divided by the square root of n. Now this is interesting. This is something we can do, but this adds another level of uncertainty to my computations. I'm doing a hypothesis test. I'm making a confidence interval. I'm trying to figure out where mu, the average of the whole population, is based on my x bar, based on my sample mean. And, well, of course, this is just from a sample, and now I've got another level of uncertainty to this because, well, I'm not really using the true population standard deviation, which I really should be using. I'm using my sample standard deviation, which is probably close to that, but it's probably a little bit above or below. And so as a result, we need a new distribution. We're no longer going to be able to use the pure, unadulterated normal distribution. Now we're going to have to use a new distribution, which is called the t distribution. So here's a graph of what some of the t-distribution looks like. First thing you need to know is it's a lot like the normal distribution. It looks like it. It has a mean value of 0. So so the peak, the mean, the median, the mode, all that, the peak is right down there at 0, and then you have positive values above that and negative values below that. It's a symmetric distribution, just like the normal distribution is. It does the same thing in positive numbers as it does in negative numbers. It also has this kind of standard bell curve shape sort of thing like that. However, it is different than the normal distribution. So you just eyeball it. You would not obviously see a difference from the normal distribution, but it is different in that it's a little bit wider. It's wider to account for this uncertainty. I'm making this approximation that probably my sample standard deviation is a lot like the population standard deviation, and so I have to account for that larger uncertainty. And so it has thicker tails going out to the sides, and the peak in the middle isn't quite as tall. The other thing is, well, this depends on my sample size. So there's a lot of t-distributions out there. There are many t-distributions, one for each different sample size. And so what we do is we measure this by computing our degrees of freedom, which in this case is sample size minus 1. So if I have a sample of size 40 out there, then my degrees of freedom would be 39, n minus 1. And what I find then is as the sample size gets larger and larger and larger, as my degrees of freedom become very large, and 100, 1,000, 10,000, 100,000, a million, what happens is the t-distribution converges to the normal distribution. So the t-distribution is different than the normal distribution if I have relatively small samples of 5, 10, 20, 30, 40. But as my sample size becomes larger and larger than larger, this curve converges to the standard normal distribution that we've all been studying. All right, let's do an example of this. This is a real data set I pulled out from a paper published back in 1846 in the Statistical Society of London, where this guy named William Guy studied lifespans, average lifespan, and he collected data on 2,455 people who were in the English gentry class. So that means they were landowners. They owned, they owned land, that sort of thing. So they were kind of upper class. They weren't peasants or anything like this. And he collected the lifespan of these, and he said, okay, I don't want to deal with children, so I only want to talk about people who'd reached the age of 21. And so he gathered data. That's a lot of data, particularly back in 1846. You couldn't just Google things back in those days. So he gathered data. He wrote a paper on it, on the duration of life among the English gentry, published this in 1846, and we still have his data to this day. First thing I want to do, before we do anything else, before we do any hypothesis tests or confidence intervals, anytime you look at a data set, you want to get a sense of it, get a feel for it. So we compute some summary statistics. The average lifespan, X bar, is 57.3. The standard deviation among all the different lifespans is 18 years. So that varies quite a bit, above 57.3, below 57.3. Other summary statistics I want to look at are a 5-number summary. The shortest duration lifespan was 21 because that's where he started counting. So he didn't count people who died at younger ages. So 21 is the minimum number in the data set. First quartile is 44 years. The median is 60 years. So half the people in his data set lived longer than 60. Half the people in his data set lived shorter than 60. The third quartile was 71 years of age. The very maximum, the oldest person in the English gentry he had in his data set lived to be 102. Way back in the early 1800s, so that's pretty cool. Next thing we want to do is look at a visualization on this on the left here. So I took this data, I fed it into R and quickly computed a box plot and a histogram. On the left, there's my box plot. So we can see the 5-number summary displayed in the box plot with a minimum of 21, maximum of 102, median of 60. There's my first and third quartiles. On the right, we can see a quick little histogram of this data that shows the distribution. And you'll notice this is not a normal distribution. It cuts off at 21 because that's where he cut things off. It reaches, so we've got kind of a peak somewhere around 60 in the low 60s there, and then it tails off pretty quickly after that. A few people lived in their 80s, 90s, and then you got that 102-year-old in there. And so that gives us a sense of what the data set looks like. Let's consider a research question. Is this lifespan different than today? Did members of the adult English gentry live a substantially different average lifespan than people in England today? Well, I hope so. It's been a long time ago, but let's find out. I did a quick Google search, found out that today the average lifespan for everybody in England is about an average population lifespan of 80 years. Now that includes everybody, whereas the study excluded people younger than 21, but let's compare that. So we're going to say, is there a statistically significant difference between this sample mean of 57.3 years and a population mean of 80 years? In other words, what we're really doing when we do these computations is I'm saying, suppose I gathered random samples of this size from the population today with the mean of 80 years. I gather a bunch of random samples. Would it be unusual? Would it be surprising to get one of those samples that would have a mean of only 57.3 years? That's what we're really computing here. To do this, we're going to do a hypothesis test. The null hypothesis, H sub 0, says that mu equals 80. In other words, the average life expectancy of the whole population is 80 years. So we're going to assume that's true. And then versus the alternative hypothesis that it's not 80 years. Again, notice that whenever we state these using proper mathematical symbols, we talk about mu, not x bar. X bar is my sample. I've got that data in my computer. I don't need to make hypotheses about x bar. I want to make a hypothesis about what mu, the average of the whole population, is. And so my alternative hypothesis is that it's different than 80. And so that's that the average life expectancy is not 80 years. All right, let's conduct our hypothesis test. First thing I need to do is compute my standard error. We've decided we're going to use the sample standard deviation divided by the square root of n. So sample standard deviation was 18 years divided by the square root of 2,455 people in that study, and we get a standard error of 1.61 years. From this, we can compute our test statistic. We take that difference, the difference between our sample mean and the population mean from our hypothesis, from our null hypothesis, 57.3 minus 80, and then we divide that by the standard error to figure out, well, how many standard errors big is that difference? The difference in age between 57.3 and 80, we divide that by 1.61 to measure that using a yardstick of standard errors, and we find that our test statistic t is negative 14.1. Hopefully at this point we're realizing, that's a big number. T is not too far different than the normal distribution usually. And so 14 standard deviations for a test statistic, just like Z is measured in standard deviation, well, so is T. So that's 14.1 standard deviations, standard errors below the mean. So what that means, if we were out there gathering samples of 2,455 people from a population with a mean age of 80, well, then getting a sample with a mean of only 57.3, that would be 14.1 standard deviations below average. Let's compute a p-value. That seems pretty unlikely, but let's do it formally. If I go to R, let's see, well, remember, we had a two-sided alternative hypothesis. We just said mu is not equal to this. We would be interested in deviations in either the positive or the negative side. And the p-value is the probability of getting the results we got or something more extreme, more interesting if the null hypothesis were true. And so we would be just as interested to have things more extreme on the positive side as on the negative side, so we multiply by 2. So we have 2 times pt is the command. It gives us probabilities from the t distribution. Pt of negative 14.1, 2454. Notice I subtracted 1 from that to get my degrees of freedom is 2454. And I get 1.8 times 10 to the minus 43rd power. This is a super crazy tiny number. If I were to write that not in scientific notation, that would be 0.000, put in 42 zeros, 1a. This is super astonishingly small. This is extremely unlikely. Way, way, way smaller than any alpha we would choose. Is that smaller than 5%? Yes. Yes, I think it is. So as a result, since this p-value is way smaller than any reasonable level of alpha, we reject the null hypothesis. We have a statistically significant difference. That difference between a sample mean of 57.3 years and a population mean of 80 years is very, very, very statistically significant. We can therefore draw a conclusion. The lifespan of the average English person today is much larger than for the adult gentry in the early 1800s when this person was gathering the data. We have a statistically significant difference. Now, okay, let's try to do something perhaps a little more useful. Well, let's see if we can put a confidence interval on this. Let's make a 95% confidence interval and see if we can say, okay, it wasn't 80, all right? We have modern medicine these days. But back in the day, what was it? What was the average lifespan of an adult member of the English gentry back in the early 1800s? It was probably somewhere close to our 57.3 that we got for our sample, but then we need to put a margin of error on that. So the formula to do that is we take our sample mean, and then we add and subtract. We do plus or minus our critical t-value times s over the square root of n, s over the square root of n being our standard error. So if we multiply our critical t-value times our standard error, we get our MOE, our margin of error, the thing we add or subtract to get our confidence interval. We need to find the critical t, the t-star value for this 95% confidence interval. Notice that this is not the same t that we got before. Before we were doing a hypothesis test, and so we got a test statistic. This is a totally different number than this. This is the number, this is the t-value we need to do in order to create a 95% interval, having 95% of the stuff in the interval, and then 2.5% in each tail, so leaving a total of 5% out of the interval. So we go to R. Then R, the command for getting this critical t-star value is QT. We're going to put in a probability, we're going to get out a t-value. So we do QT of 0.975, having 97.5% less than us, and then 2.5% to the right of us. Our degrees of freedom, we have to put in the degrees of freedom because there's a different t distribution for every different level of degrees of freedom. Our degrees of freedom are 2,454, and that will give us exactly the same thing as what we would get if we did minus QT of 0.025 of 0.0252454. Okay, so if we leave 2.5% in the left tail, both will give me the same result. It's 1.96, which is about what we would get from the normal distribution, because we have a pretty large sample size here. So this is come pretty close to converging to the normal distribution. Let's compute our margin of error. Our margin of error is our t critical value, 1.96, times our standard error. We did that before. That was 1.61 years. 1.96 times 1.61 years is about 3.2 years. So that's our margin of error. We add and subtract that to our sample mean of 57.3. And so that means our range goes from 54.1 to 60.5. Based on this data, we are 95% confident that mu, the true population mean, the average lifespan of all adult English gentry in those years before 1846, was between 54.1 and 60.5 years. All right, so to summarize, oftentimes we will have numerical data where each element of our sample gives us a number. Now, we can use the t-distribution to perform hypothesis tests and compute confidence intervals to tell us something about what the true mean of the whole population is, using our sample mean x bar and sample standard deviation s, but only if the sample size is larger than 30, or if the underlying population is at least approximately normally distributed. Whenever we do this, we will make the approximation that the standard error is our sample standard deviation divided by the square root of n. Whenever we've got a sample standard deviation, not a true population standard deviation there, we have to use the t-distribution rather than the normal, the z-distribution. To do a hypothesis test, we compute our test statistic, t, as being our sample mean x bar minus our mean of the population, as given by the null hypothesis. We take that difference and then we divide it by the standard error. And we can compute a confidence interval by taking our sample standard deviation, our sample mean x bar, and we add and subtract our margin of error, which is our critical t value, times the standard error.